This playlist will collect together and organize the individual component modules, which together will comprise our lecture on Turing's article, Computing Machinery and Intelligence. The storyboard for this lecture will have three major acts. We'll start just by reviewing Turing's discussion of intelligence and his proposal called the imitation game, which ultimately gets renamed the Turing test. Once we complete our discussion of Turing's imitation game, then we'll turn our attention to the second act, in which we look at the challenges, or at least some of the challenges, that Turing raises to his view in the context of his paper and the responses that he gives in the paper. Finally, we'll step outside of the paper in our third act and consider some of the myths and misunderstandings regarding Turing's view that have promulgated throughout the philosophical and wider literature. So let's shift our attention now to that first component, looking at how Turing introduces the notion of thinking and his imitation game. Turing starts off the paper by saying we oftentimes ask whether or not machines can think. He wants to reject this question as ill-formed and ambiguous and not capable of being answered in any interesting or useful manner. Instead, Turing urges us to reject this question and substitute in a different, well-formed question, a question which could be decisively answered by a simple test. So the first move that Turing makes here is to claim, look, we can't resolve these questions like can a machine think precisely because they're formulated in a manner in which there is no clear-cut evidence that we could bring to bear that would prove decisively yes or decisively no. What we need is to formulate a question in a way that operationalizes it, that gives us a means of creating an experiment that would allow us to bring evidence to bear upon its solution. Now you might say, now, how could we resolve such an abstruse metaphysical debate with a simple test? And this is the second component of Turing's solution, in a way, a component that he borrows from Ryle. What Turing suggests here is that, look, if we need to resolve this question, then we need to appeal to evidence that we can generate and which will be accepted as having high evidential warrant. So what we want is evidence that everyone will accept for intelligence. And he thinks when you look at people's behaviors, you regularly make judgments about whether or not those behaviors are indicative of intelligence. Now, we might recognize this line of thought from Gilbert Ryle's The Concept of Mind. On page 27, for example, Ryle tells readers when a person is described by one or other of the intelligent epithets, such as shrewd or silly, prudent or imprudent, the description imputes to him not the knowledge or ignorance of this or that truth, but the ability or inability to do certain things. And this is the essential element of Turing's proposal, the idea that if a machine is successful enough at imitating our performances, those imitations are in fact instances of the performance itself. They are just as worthy. They provide just as much evidence for intelligence as they do when the human being exhibits those same behaviors. Now, to harness our dispositions to judge intelligence on the basis of performance, Turing wants to keep our anthropocentric standards for success and failure that we use in those judgments, but to get rid of all the other anthropocentric elements, those biases against non-humans that might creep into his experiment, so that we judge the performance based on our perception of its meeting our standards for success, that is, for being indicative of intelligent behavior without being biased by differences between computers and ourselves. Thus, Turing suggests that we can adapt the British parlor game, the imitation game, or what we might call the chat room game nowadays, to create our experiment. We'll have 3 participants, 2 human beings and 1 computer. To prevent any of our biases from tainting our data, we'll separate the participants off into their own rooms, allowing them to interact with each other only through what he calls these teletype terminals or text messaging. One of the participants, one of the human participants, will serve as the interrogator and will ask questions of the other 2 participants. When a sufficient amount of time has passed, a bell will ring and will ask the interrogator to make a judgment. Which room contains the computer and which room contains the other human participant. Once each of the participants is ensconced or isolated in their separate cubicles, the game proceeds largely as a wide-ranging conversation. The interrogator asks any questions that he or she deems appropriate or useful for trying to determine the identities of the participants, and the person and the computer are going to answer in accordance with their desires and understandings of their programming and so on. At a certain point, a bell will ring, our experiment or operationalization, the game is over, and the interrogator then is going to guess on the basis of the questions they asked and the answers that were given which room contains the computer and which room contains the human being. Thus, as Turing portrays his experiment in the paper, we have 3 participants, 2 human beings and a computer. One of the participants serves as an interrogator, the other participant serves as the second subject. They are cloistered away in their isolation chambers and they can communicate only through text messaging. The interrogator is free to ask any question that he or she would like. The computer and the human being then answer. As time goes by, eventually a bell rings, the experiment is over, and we ask our interrogator to make a judgment. Which room contains the computer? Which room contains the human being? Now, presumably, at least sometimes, the interrogator will guess incorrectly. But certainly not always. Sometimes the interrogator will probably guess correctly. We then take all of that data, each of those individual iterations of our game. If, when we pull together all of those experiments, we collect together the choices made by our interrogator and all those different times we played the imitation game, Turing says we'll have strong evidence that machines can behave intelligently, that machines are intelligent, if about 70% of the time the interrogator guesses right and about 30% of the time the interrogator guesses wrong. Now you might think, oh, that's pretty random. Why pull those numbers out of the air like that? Or you might think, that doesn't seem like very good evidence. But I think we can reflect on the nature of our experiment here and realize that the numbers aren't really random, and they provide us with a pretty strong bit of evidence. Suppose our hypothesis, or Turing's hypothesis, is false, and that machines cannot in any way, shape, or form behave intelligently. Well, then we would expect our interrogator to get it wrong 0% of the time, or about 0% of the time. If they can't behave intelligently, then we can recognize that quite easily. What about if Turing's hypothesis is true in the best case scenario? Machines behave so well, so much like we do, that we can't distinguish our behavior from their behavior in this Turing test imitation game scenario. Well, then we'd just be guessing 2 rooms, 50-50. So our range of possible values here between false and true is actually between 0% incorrect and 50% incorrect. If we imagine that, hey, machines can behave intelligently without actually behaving so indistinguishably from us that it's just a matter of chance whether or not we're guessing right. And so the middle point between that would be about 25%. And so what Turing is suggesting is, look, we'll have good evidence for my hypothesis if, in fact, what we discover is that machines behave much better than the false hypothesis prediction. That is, the hypothesis that they can't behave intelligently. They're not quite as good as human beings, but they're better than the midway point, right? So they're significantly above the hypothesis that they can't, even if they're not quite to the hypothesis that they're indistinguishable from us. And we'll pick this up, talk about the objections next time.